am Kshitij and we will be talking about moment of inertia. So, moment of inertia is a very important topic in physics. Now, bear in mind that we will be talking about this topic in reference to NEET physics, although people from CBSE and JEE can benefit a lot from this as well, right? So, a bit about me before I start. I am Kshitij and I have been teaching physics for quite some time, and I have given quite good results in this subject. Alright, now let's start. So, moment of inertia, right? So, it's made up of two words, moment and inertia. What does moment mean? Moment it's basically a measure of the impact of a physical quantity based on the distance, right? So, how do we do that? How do we measure it? So, imagine there's this distance r, right? And the body being impacted is right here. Let's call it P, right? So, some kind of force acting here, right? Some kind of force acting at this point, let's call it X. Now, the action of this force acting at this point along this distance, right, will provide an effect on point P. Now, that will be called its moment, right? Now, we have different kinds of moment in physics. Primarily, this being the moment of inertia, we have dipole moment, this can be a magnetic dipole moment or it can be electrostatic dipole moment, right? Right? We have dipole moment and then we have torque, right? Torque. Now, as we are talking about moment of inertia, so torque will play a very important role, right? So, as I talked about right now, moment of inertia is made up of two words. I explained what moment is. Now, let's move on to the second part, that's inertia. So, as we all know, inertia is the resistance of a body towards change in motion, right? So, classical inertia, it provides resistance in linear motion, right? Linear or rectilinear or translational, you can call anything, right? Moment of inertia provides resistance in rotational motion. Rotational motion, correct? So, you can think that moment of inertia is essentially the same thing as mass, right? Let's do the analogy. So, when we talk about inertia, right, we have mass in linear motion, we have moment of inertia in rotational motion. Moment of inertia is represented by just using the capital letter I, right? So, let us think about it. So, when we talk about kinetic energy, right? So, what's the formula for kinetic energy in linear motion? It's half into mass m, and square of the velocity of the moving object, right? Similarly, when we talk about rotational kinetic energy, the formula becomes half, instead of mass we have inertia, right? And instead of velocity, now as we are talking about rotational motion, this becomes omega square. Omega is nothing but angular velocity or rotational velocity, correct? So whenever we talk about rotational motion, right, thing is, anything that you, in any formula, in any place, wherever we talk about mass, we will replace it with moment of inertia, right? So, now we talked about what is inertia and we compared it with moment of inertia, like linear and rotational. So, as I mentioned, we will be talking about torque. Now, funny thing is, torque is also a moment, right? Just like moment of inertia. It is a moment of force, and that's what we call it alternatively as well, right? So whenever you do the paper, right, you attempt the paper, you attempt the exam, if you see this terminology being used, they are essentially talking about torque, right? So why this term? Why do we call it moment of force? If you remember from before, we were talking about distance, this body right here at point P, right? And the force acting on X, right? So this distance and this body and this force. Now if we think about it, this force is being provided, right? So this torque, it becomes equal to the cross product of the distance and the force being provided, right? So this is what is torque. Right? Torque. This is a Greek letter, it's called tau. So we represent torque with this Greek letter tau, right? Now, how is this related to moment of inertia? Another way we can represent torque is you can realize it by just doing the analogy, right? So we talked about linear motion, right? So if a body is not in uniform motion, there has to be some kind of acceleration on it, right? And if acceleration is there, so there is a force acting on it. For that force, that formula is mass times acceleration, right? Similarly for torque, that torque is the moment of force, right? So instead of mass, we get inertia, right? Moment of inertia. Instead of acceleration, we have angular acceleration. Angular acceleration is represented by alpha, right? So this is the relationship between torque and moment of inertia, right? Now before we proceed further, there's a very basic principle that operates when we talk about rotational motion and in a moment of inertia. It's called the principle of moments. So according to that, a body is in a state of rotational equilibrium when all the forces, all the moment of forces acting on it is zero, right? So basically, if we have a body right here, okay, and there is a torque acting in this direction, and another torque is acting in this direction. Let's call this one T1 and this one T2, right? So the sub net total of these two torques should be zero. Then that body is in rotational equilibrium. That's what the principle of moments says, right? Okay. So we talked about torque. We talked about its relation with moment of inertia. Now let's move on to moment of inertia itself. So when we were talking about torque, torque is if you can imagine it as a rotational force, right? But it's not exactly force, it's the moment of force. So the force is acting in this direction, the torque is acting in this direction. So imagine this body is there, right? And I mentioned that it's the equivalent of mass in rotational inertia. So therefore, what's the purpose of moment of inertia? It will resist this torque, right? It will not allow it to move easily, right? Just as mass. So imagine if you are pushing an object, right? If it's imagine it's of 10 kg, So if you push it, it requires some amount of force, right? But if it's heavier, you need more force. Similarly, as mass acts in linear motion, so if I'm pushing it like this is linear motion, right? But if, imagine this cup is there, right? I have to push it like this, right? So this is the torque, okay? So it's rotating like this because of the torque I have applied on it, right? So the moment of inertia of this cup, it will resist that, just like mass resists force, right? Okay. So imagine, now in physics we always start from smaller systems, right? So if we talk about moment of inertia, imagine you have a particle, right? It has mass m, okay? And the axis of rotation is right here. Let's call it A and A dash. Okay, this is the axis of rotation. What that means? So imagine this is that cup right now, and it's rotating like this. This cup is rotating like this. This is, imagine this is the cup, right? This is the equivalent of this. Okay, so imagine the cup is, this is that cup in that state, just like that, and it's rotating like this. Okay, so this thing becomes the axis of rotation, that is A and A dash. Okay, now imagine that cup that cup is a small particle of mass m. Now if we take the perpendicular distance of that mass from the axis of rotation, we can call it r. Therefore the moment of inertia of that cup, it becomes mass times the distance squared. Okay, right? Now this was just now when we talk about moment of inertia for bodies, it's not just made up of one particle, it's made up of different particles. So imagine there are several particles, right, with different distances. So the moment of inertia for them, it becomes the vector sum for all of these, right? So m okay, sorry, right? Now as you can see, moment of inertia also follows the principle of superposition. You can see in that, right? So this was the formula for the system. Now we have different kinds of bodies when we talk about moment of inertia in this competitive exam, right? The first one being uniform linear rod. Okay, so when we talk about this body, imagine that you have a rod of length L and mass m, alright, and the linear mass density is represented by lambda. So then lambda becomes equal to mass by length, that is n by L. Okay, now as you imagine that when you were talking about the particle, so there was some distance between the particle and the axis of rotation. Now if you recall, for a uniform linear rod, the center of mass is at L by 2, right? So for moment of inertia passing through the center of mass, right, we have this distance L by 2. Okay, so let's start from here. Now let's derive the formula for the moment of inertia of a uniform linear rod wherein the axis of rotation is passing through the center of mass from that linear rod. Now as it's passing through the center, let's just take this part, okay? This length. So R is here, L by 2. Bear that in mind before we proceed further. Just write it down separately. Now take this into account that this mass is a collection of several different bodies, right? It's a continuous mass distribution. So let's just take a small mass here of length dx, right? And it's from a distance of x from the center of mass, from the axis of rotation, alright? So if you take into account this, the moment of inertia for this point mass becomes di, right? And what's that equal to? Because this is a particle, right? This becomes, if you remember the formula, if you recall the formula, it's mr square. So the distance is mx square, right? Sorry. Yeah, it's dmx square, sorry, dmx square. Because the mass of this point mass will be dm, right? So it's the moment of inertia for this particular particle becomes dmx square, right? Now, but we want the moment of inertia for this linear rod, right? So we will have to integrate this. So for integrating this, after integrating this, we get the moment of inertia for this rod, right? And what's that equal to? That's equal to the integration of dm multiplied by x square. But here's the problem. We can't integrate dm, right? We have x square, we need to integrate that. But there's a dm, we need dx here. For that, think about it. I mentioned before this linear mass density, right? This linear mass density, what this means is the mass per unit length. Therefore, the mass per unit length is m by l, okay? So for 1 unit, the linear mass density, it is m by l, right? Or lambda, right? This is when if you multiply it by 1, that's the length, right? So what this becomes? The mass here becomes lambda for 1 unit. But if you talk about dm, what's the length for that? That becomes dx, right? The mass for this, it's dx into n. So therefore that becomes, for dx units, it becomes lambda into dx, right? So lambda into dx, what's that equal to? That's equal to lambda dx. So just we put this value here, and what we get? I is equal to lambda dx into x square, right? Okay, so this is a constant, so this does not stay here, it comes out. So we get lambda dx into x square, okay? Now this looks integrable, right? But remember, right now we are only talking about this part. So we have to multiply it by 2. But before that, we have to set the limits. Just take a second to write this down. Then I will add to the board. Okay. Right. So we have this, and we have to set the limit. So right now, just think about it and imagine this is the origin, right? So this becomes 0 on the x-axis, this becomes L by 2, right? So we get the limits for this integration. 0 L by 2 dx, let's just for convenience, let's just call it x square dx, okay? So we get this, but this is for only half the rod. All we need to do is just multiply it by 2. Right? This looks doable and it's for the whole rod. Instead of using 0 to L by 2 and using this 2, you can just do minus L by 2, integrate from minus L by 2 to L by 2, and you don't need this 2 then, okay? Or you can just integrate from 0 to L, your choice, right? So moving further, if you integrate this, you get x cubed by 3 with the limits L by 2 and 0. Now 3 is a constant, so it comes out. So you get 2 by 3 lambda, right? And since it's 0, we can just put the input the value directly into x cube. So we get this cube of L by 2, right? What that becomes? Okay, we cancel this out, and this becomes L cube lambda into 12. Yes, but if you remember, lambda was m by L, so we input that L cube by 12 into m by L. The final product, the final value for the moment of inertia for this body will get is ml square by 12. Okay, so that's how we get the derivation of the moment of inertia for a uniform linear rod, right? If you want to look at the exercises, just pause the video and it will be fine. Okay, moving on. So when we talk about moment of inertia, we have different theorems. There is a theorem of parallel axis. And there is a theorem of perpendicular axis, right? So when we talk about the theorem of parallel axis, what does that say? So imagine for a continuous mass distribution, the moment of inertia is passing through the center of mass, okay, and another axis is just parallel to this axis of rotation. Let's call it this one A dash, and let's call this one B dash. Okay. So what this theorem states that if we have the moment of inertia for this axis of rotation through the center of mass, then the moment of inertia for the parallel axis, it becomes equal to the moment of inertia for A dash, right, plus what? You see there's a distance between them. There's a perpendicular distance between them. Let's call it A. Okay. Right? So this becomes A dash plus mass into A square. Mass of what? This body. Okay. Similarly, we have the theorem of perpendicular axis. Okay. What this states. Now, before we move on to the theorem of perpendicular axis, this theorem is valid for 1D, 2D and 3D bodies. All three kinds of bodies, right? But when we talk about the theorem of perpendicular axis, it's valid only for 2D bodies. So, what's the theorem of perpendicular axis? Imagine that your body is a 2D body, right? And it lies in some kind of plane, a 2D plane, okay? So let's call this one X, this one Z, right? So we have a moment of inertia passing through the center of mass, right? But in this plane, okay? And another just perpendicular to it. So let's call this one X dash, and this one Z and Z dash, okay? So if you see, the theorem states for this third axis passing through, that's just perpendicular to the mass, the body, right? let's call it y dash, right? So I for y dash, it equals to the I of x dash plus I of z dash. Keep in mind that this body is in the xz plane, right? And this is passing through the center of mass, all three axes. That's when this theorem of perpendicular axis takes place. Okay. Next, I'm going to write down the moment of inertia for different bodies, right? Okay. So we talked about the mass of the moment of inertia for the uniform linear rod. Okay. So for a rectangle, the axis of rotation passing through the center of mass, it becomes m into L square plus P square by 12. So this is the length, this is the breadth. Okay. Now this is when it's passing perpendicular to the plane. Okay. Next, we have a square. For the square, the value is ma square by 6. Here a is the side of the square. Alright. For triangle, this one's interesting. It's a bit different, but not really. Okay. So imagine there's this triangle of height h and a base b. Okay. Now imagine the axis of rotation is along the base. In that case, the moment of inertia for this body, it becomes m into h square by 6. Alright. Then we have the most basic body, which is used all throughout our NEET physics. It's called the ring. What is a ring? Basically just a hollow circle, a hollow disc. So we have this ring, there's nothing inside it. Okay. So for this, if the axis of rotation passes through the center of mass of this ring, this becomes the fundamental formula. Okay. R is the radius of this ring. Now, if this were not hollow, if this were filled, it would be called a disc. So for a disc, this becomes, okay. Now, this formula is same for a hollow cylinder and a solid cylinder, right? So let me rub this first. So if we talk about a cylinder, okay, but hollow, and this is solid. Solid is the filled one. Okay. So imagine this cylinder is standing upright. Okay, and the center and the axis of rotation is passing through the center of the upper surface area of the cylinder, right? If the cylinder is hollow, the moment of inertia is mr squared. What's r here? The radius of the upper surface area or the lower surface area. Similarly, if the cylinder is solid, it becomes mr squared by 2, right? In a similar manner, for cone, the moment of inertia is mr square by 2. Now it's the same as the disk, but I would recommend you not to remember it like that, because then it might cause confusion. In use cases, practical use cases and applications, hollow cylinder and ring are used interchangeably, and disc and solid cylinder, they are used interchangeably, but not this. Okay, so please remember that. Now this is the moment of inertia for our hollow cone, but if it were filled, if it were solid, this would become 3 mr square by 10. Now for a sphere, okay, the moment of inertia two by 3 mr square. But keep in mind, this is for a hollow sphere. Okay, it's also called a shell. For a solid sphere, this formula, it becomes 2 by 5 mr square. A solid sphere can also be called a ball in terms of the exam. A ball may not necessarily be solid, but if for this case, for this exam, it's referred to as a solid sphere. Okay, that was a bit too much on derivations, right? On the different formulas. Okay, let us talk about the radius of gyration. What's the radius of gyration? So imagine the axis of rotation is right here around this body, okay, and this is the center of mass. We don't need to imagine, but just imagine, because it's not, this radius of gyration thing is not necessarily for an axis of rotation passing through the center of mass. Okay, so let's just see, for this body there is an axis of rotation about which this body is rotating, right? It has it has a mass distribution in different places. Okay, now what is the radius of gyration? The radius of gyration is the perpendicular distance of an axis of a point P, where at that point P, if you concentrate that mass distribution, that moment of inertia will be the same. Okay, so if the mass for this body is m and you have the radius of gyration, that is k, right? The moment of inertia for that body becomes mk square. It's irrespective of what kind of body we are talking about, which shape it is, whether it's 1D or 2D or 3D, alright? This is very important. Okay. So all of this, it converges down to this, right? Now you remember this formula. This moment of inertia is equal to mk square. Okay. Now a very important application for moment of inertia is rolling. Rolling is basically when a body has translational motion and rotational motion at the same time. So for rolling, the kinetic energy formula, we are not going to talk in detail about that because that's outside the scope of this. I'm just trying to connect the dots, right, so that this topic is comprehensive. So the kinetic energy of rolling is equal to the kinetic energy of the translational motion, and added to that is the kinetic energy of the rotational motion. Okay, so this becomes half into mass into velocity of center of mass. Why not velocity? Why velocity of center of mass? Because you have to keep in mind that the body is in rolling motion, so it's constantly rotating and moving forward at the same time. So this is the point of reference we have, okay, the center of mass velocity. and that's anyway that's what we calculate. So talking about the rotational motion, if you remember from before, the kinetic energy of the rotational motion is half into the moment of inertia multiplied by the angular velocity square. Okay, so this is very important. Now if you enter this into this and you input the value of the angular velocity, the relation of the angular velocity with the linear velocity, so that's linear velocity is equal to the r multiplied by omega. So omega becomes v by r, right? So omega square will become v square by r square. So what we get is half m v square plus half m k square v square by r square. Again, this velocity is the velocity of the center of mass. Okay. Now if we take this common, what do we get? We have half m velocity of center of mass square, right, plus k square by r square. Now we can note this down. Now the ratio of KE total, okay, when compared to rotational and to linear, okay, you can get from this. So what would that be? For linear we have 1, for rotational we have k square by r square, and for total, that is the rolling, we have 1:1 plus k square by r square, right? The last thing for today, now as you remember, for the solid sphere, the moment of inertia was 2 by 5 mr square. At the same time, if you take into account the radius of gyration, the moment of inertia formula becomes this, right? So what does the radius of gyration become? It becomes root of 2 by 5 into r. Alright, why I have mentioned this? So take into account, now this is something which is a combination of many things, but this is important to this topic, so please bear in mind, right? So imagine you have an inclined plane, right, and a body is rolling down this. So let's take in mind a solid sphere, okay, then we have a disc or hollow cylinder, or sorry, solid cylinder, right? Then we have a hollow sphere, right, and we have a ring, okay? So when we talk about this, we are not going to derive the formula for this right now, just to give a comparison vis-a-vis the moment of inertia. So time to reach bottom, that's t, time to reach the bottom. Acceleration of that body, the tangential acceleration, and the radius of gyration. Okay. So as you can imagine, if the time increases, the acceleration will. If the time increases, the acceleration will decrease. But if the time it decreases, the acceleration it will increase. Okay. What will happen to the radius of gyration? So for the solid sphere, this is root of 2 by 5r. For the disk, what is it? It was mr square by 2. So therefore it becomes root of 1 by 2 r. But we can't really compare this, right? We can just write 1 by 2 as 2 by 4, right? You can see it's increasing along with the acceleration. Similarly, we have for the hollow sphere root of 2 by 3 r, and for the ring 3 by 3. This is just r, so you can write it as like this, right? So this was all I had to teach for today. Before we end the video, right? Before we end the video, I have around 3 questions. So you remember when we were talking about the linear rod, right? Linear rod, the axis of rotation was passing through the center of mass. Now this was in this plane, right? I want you to calculate the moment of inertia for this, for the first thing, for the edges, right? For the edges in this plane, and the moment of inertia when the axis of rotation passing through the center of mass but perpendicular to this plane. Okay, so edges perpendicular to plane. So 2 questions for everyone who is watching this video. One question for especially for those who are preparing for NEET exams right now and have already gone through the syllabus once. So this question is an important question. Okay, write it down. So if a body is rolling on a level surface, right? Imagine it's rolling. So if a body is rolling on a level surface, there is no incline, okay, and the kinetic energy of rotation is equal to the kinetic energy of the linear motion, what will that body be? Don't think about friction here, okay, and there can be more than one answer. All right, keep your answers in the comments, post them. And we'll see you next time. Bye bye.